Hey, good afternoon. So I'm Stuart Baird, and with me is Tristan Entz and Riker Steiner. And today we are going to be talking about one of the major impacts with backpacking, the jet boil system, and how we can have a more efficient way as backpackers to cook our food. So overall, we'll be discussing how we can make adventures great again. So to begin with here, on the left is a picture of our jet boil. Now it holds about 500 milliliters of water and has a propane tank on the bottom. And essentially what we're going to do here is that we heat up the water, and because it's insulated, it boils the water very quickly. This is great, but it also has a couple of concerns, such as overboiling. So our objective here is to simulate a controller for the jet boil system so that we can boil the 500 milliliters of water without causing an overflow situation. The overflow is bad because, if you're in the middle of nowhere and you get serious burns on you, that can be a potential safety issue. And we also want to be able to control our boil. So we want to be able to get the water to the boiling temperature at a controlled speed. So the first thing we did is we collected data. So with this, we set up our experiment, and how we set up our experiment is we used a K-type thermocouple. We chose this because it was great for the temperature range that we were using, which is boiling water. And we hooked it up. So one end went into the water, the other end went into a device that gathered and stored the data. And it provided us graphs. And the information that we received are in the pictures or the figures on the left-hand side of the screen, which is the set point and the temperature, time. We also were able to get the temperature versus time. And with the set point, we first started it at 100% open so that we can get close to that the boiling temperature of water, which for our altitude is 95 degrees Celsius. We wanted to get as close as we could as possible. So we started off with the set point being 100% open. And then as we started to approach that temperature, we began to decrease the set point. So first, at about 120 seconds, we set our set point, or we decreased our set point down to 50%. And then 30 seconds later, we decreased it again down to 25. And the reason we did this is that we're still increasing our temperature of the water, but we're doing it at a more controlled rate so that we can not have an overboil situation.
We took that data that we have recorded from the experiment and we decided to fit that to a first order plus dead time empirical model. We decided to do this instead of a physics-based model for simplicity of not using the energy balance. So on our graph for our output, we have that black line, that is our process data. We have a blue line, which was our initial guess, and then we optimized that through our programming, which produced our red line of our optimized FOPDT model. That model then gave us the values of Kp of 3.727, a tau p of 726.948, and a theta p of 9.619. Here we also have our input data, the blue being what was measured, and the red dotted line, which was our interpolated program to follow that.
So once we have those FOPDT parameters, Kp, tau p, and theta p, we then can use them to tune a PI controller. Now the reason why we chose to use a PI controller instead of a PID controller is because our system is just reaching up to a boiling point, up to here in Provo being 95 degrees Celsius is where the boiling point of water is, and it's not dropping back down. We don't want the temperature to drop back down. And so the derivative constant dampens oscillations and helps when you are trying to go back down to different set points. And so we found that a PI controller would work just fine and that we would not need to use the derivative term in our system. So that's why we chose a PI controller instead of a PID controller. Now, like I said earlier, using the Kp, tau p, and theta p values, we then were able to use the IMC tuning correlations and those values to obtain Kc and tau I. The Kc values that we calculated using moderate tuning was 2.215 and a tau I value of 824. The graph to the left shows the results of our PI controller tuning, and it shows that at about 1 minute of the valve being 100% open, you can begin to shut the valve, and you can steadily begin to shut the valve after about a minute of running till about 3 minutes of running the system, at which point then you will have reached the boiling point of water and not have gone through an overboiling part.